Hi, hi, hi. Okay, this is part one of two. So I'm doing the first video just on neurophysiology, and then and I'm probably focusing a little bit more on anatomy than y'all need for your MBME. But I do find that it's helpful to understand like the geography and landscape of the brain, to understand strokes and tumors and the effects that they'll have on proximal tissue. The second video is going to be more on pathology, and that's probably a little bit higher yield for your MBME. But again, I think it's if you have a nice foundation with this first video with the neuro, then the pathology comes a little bit easier. Okay, let's get in. All right, so we're going to start with like a big picture overview, talking about the cerebral cortex, introduction to subcortical structures, and then we're going to go into more depth on each of these: basal ganglia, dopaminergic pathways, limbic system, thalamus, hypothalamus, pituitary axis, the cranial nerves, the brainstem, cerebellum. We're kind of moving like, superior to inferior as well, if that makes sense. Going into the spinal cord. Then we'll talk about the vasculature, which is really high yield to understand strokes, the meninges, the ventricular system, and then the venous drainage, which the three of these kind of go together. And then just a couple things about cell types and the peripheral nervous system and embryology. All right, so a lot of people can. It's fun. It's fun, colloquial, conventional science to talk about the triumvirate brain, right? Where like the bottom part of the brain is the reptile, and then we have the limbic system, which is the mammalian brain, and then the neocortex is all of the complex thinking. And I don't know, maybe there's like a shred of truth to this, and it's fun to talk about just in like dumb bar conversations. But the brain, obviously, as we're going to go through, doesn't really work so much like this. Similarly, people kind of overhype the differences between like the left brain and the right brain. The left brain is so rigid and mathematical, and the right brain is all artistic. Again, probably some shred of truth, and I'm definitely not the guy to really answer that debate. But again, I think it's overblown. What you should know is the left brain typically controls the right muscles. The right brain typically controls the left muscles. There will be exceptions. The language center is typically, but not always, on the left side of the brain. And just to really highlight, you can have a hemispherectomy. You can take out one entire lobe of the brain and you're still fine. The truth resists simplicity, right? Like we've talked about the triumvirate brain, the left versus right brain. So a lot of the borders that we're going to see are going to be fuzzy, right? So when we say, oh, the parietal lobe is for touching, well, the other parts of the brain are also going to have a role in touching as well. It's just that the right part of the parietal brain might play a larger role in touching than other things, et cetera. All right, so let's get in. Here's the brain. Let's do it. I made a bunch of dumb videos, so we're going to have to suffer through them. Okay, so the calvaria are the parts of the skull that border the brain, and that's where the cortex of the brain is named after. So here we're looking at the frontal bone covering the frontal cortex, and then you'd have the parietal bone covering the parietal cortex, et cetera. Those are calvaria. All right, so we open it up. We have two dural layers, a cranial dural layer, and then an intermeningeal dural layer. That's important. Then the arachnoid layer, and then the pia matter of the meninges, which is not shown. So let's go below the cortex, looking at all the subcortical structures under the cortex. We have the falx cerebri, which we'll talk about. It's a dural layer. The corpus callosum, left and right communication, the lateral ventricle. Here we have the basal ganglia with the caudate nucleus and the putamen. Then the tutorium, which is also part of the dural layer, very similar to the falx cerebri, and it's going to we're going to have subtentorial and supratentorial structures. It's a way that commonly we will talk about the geography of the brain. Okay, so the cerebrum. Cerebrum really just means the cerebral cortex plus the basal ganglia and parts of the limbic system, which is there's not as much unity in the limbic system as there is compared to the basal ganglia. Here in the back, we have the little brain, the cerebellum, and then of course the spinal cord and the brainstem, and these gyri and sulci, which we can talk more about right now. So yeah, we've got a left hemisphere or left hemisphere and right hemisphere. So the sulci and the gyri, I would just think of them as like a mountain and valleys, right? So the valleys is going to be the sulcus, and then the mountains on either side are going to be the gyrus. The periphery of the brain, we have the gray matter. That's where the axon body, the somas, the neuron bodies are going to be. And then the white matter is where the axons are. You can see a picture here a little bit better. And this kind of makes sense if we imagine that everything's going through the spinal cord, through the brainstem, and it's trying to make its way to the periphery where these, headquarters cells are. It would make sense, in my opinion, to have the soma, the cell body on the outside. Notice that, though, this is the opposite of what we see when we're looking at the spinal column. Here we're going to have the gray matter, the cell bodies on the inside, and the white matter on the outside. So the frontal lobe is going to be for complex thought, emotion, and motor function. We have a density of motor function in the somatosensory cortex of the frontal lobe. Parietal lobe is for feeling and touching, and we're going to have a density of feeling, touching neurons in the somatosensory cortex, which borders the somatomotor cortex. Occipital lobe is going to be for vision. Temporal lobe is going to be for hearing, a little bit of emotion, a little bit of limbic system. We have this Sylvian fissure right there. That's going to be important to separate the frontal lobe from the temporal lobe. And then we're going to have the Sylvian fissure is also known as the lateral fissure. Then we have the central sulcus, which is going to separate the frontal lobe, parietal lobe, more specifically the somatomotor cortex from the somatosensory cortex. All right, so I recorded these and I didn't realize I had the sound on. So you guys are going to, if it wasn't evident what a nerd I am, you're going to hear the music that I listen to on Spotify while I'm doing this. So this is just a video showing the Sylvian fissures, lateral fissures, and then the central fissure. Cool, epic. All right, so most people are right-handed, 90% of the population. And if you're right-handed, again, we said that there's this kind of like, right-handed people goes to the left part of the brain. So if you're right-handed, your left brain is dominant. And so then the language center will be on 95% of right-handed people. Now, if you're left-handed, that means that your right brain is dominant. But it's weird that, again, even if you're left-handed, the right brain is dominant, you still typically have the language center. So for left-handed people, 70% of people are still going to have the language center on the left side. Again, that's really important for Broca's area, which is kind of for like speech production, and then Wernicke's area, which is for like speech comprehension. So when in doubt, it's just safe to say that the language center will be on the left side. All right, so we're going to listen to Broca's aphasia here on the left, known as non-fluent aphasia, because they can't speak fluently, but there is meaning behind what they're saying, as opposed to Wernicke's, which we're going to hear on the right, where people can talk fluently, hence fluent aphasia. They can speak and say all they want, but not a lot of like content is really coming out. So let's go ahead and listen to this guy on the left. He's talking about how he had a stroke and he started a support group and the amount of people he has in the group. So let's take a listen.
Founder for me, and members.
Notice how hard they're struggling to find the words.
How
long it takes.
Members, probably 60 people.
So 60 people are part of Voices of Hope.
Yeah.
Okay, let's listen now to Wernicke's aphasia and just notice the contrast.
Hi, Byron. How are you?
I'm happy. Are you pretty? You look good.
What are you doing today?
We stayed with the water over here at the moment and talked with the people for them over there. They're diving for them at the moment. They'll save in the moment. He'll have water very soon for him. With luck for him.
So notice that like the words per minute in Wernicke's aphasia is not so different than it would be for someone who hasn't suffered a stroke, but the content, the meaning is a little bit lost, right? There's some meaning you can connect. He's on a cruise and people are swimming and they're happy, and like you can, and maybe the girl's pretty he's talking to, but like it's not as sensible as a Broca's aphasia. All right, we're gonna hear more dumb music. So this is just showing the difference between the precentral and postcentral. Precentral in the front, and postcentral on the back. Okay. So when we're looking at the precentral and postcentral, again, divided by the central sulcus, we have this homunculus where things kind of in the medial side are going to be more like your legs. And then things on the lateral side over here are going to be more for the face and the upper arm extremities. This is going to be really important when we're doing ACA versus MCA strokes in the future. So the homunculus, you have more nerves dedicated to things like your hands and your lips, and that makes sense. You got to feel where you're going. You have to differentiate like a sharp object versus like a smooth object, and same with your lips. Something hot is something cold is something poisonous, etc. And then maybe something like your like left oblique doesn't really need as much like high octane like sensory differentiation. And so, yeah, we're going to, feeling, you can read Braille, you can eat ice cream, you can differentiate. And so if your, homunculus is functioning, you should be able to feel things. And if it's not functioning, you have an ACA or an MCA stroke, you're not going to be able to touch or feel or move muscles or and whatnot.